Okay, today I'm going to introduce you to something called polar coordinates. Let's look at a point in the xy plane. Okay, suppose you have a point, how about, let's put it right here. And let's just call that point xy. Okay, now these are called rectangular coordinates, xy, because what do? We count the number of steps over along the x-axis, right? And then that becomes your x coordinate. And then we count the number of steps over, or rather I should say up, the y-axis, and that becomes your y coordinate. If I were to do this to connect those, see, it forms a rectangle. So those are called rectangular coordinates. Okay, now there's another type of coordinate system that you can use, which is called polar coordinates. Whoops. Okay, and let me show you what polar coordinates look like. Okay, what you do is instead of measuring over and up, or up and over, either of those would work, right? In rectangular coordinates. In this new coordinate system, what you do is you measure two things. Number one, you measure the radial distance from the origin out to your point. And we'll call that r. And then you measure the angle from the positive x-axis counterclockwise to that radial segment. Let me fix that. There we go. Okay, we're going to call that theta. And then that point there, which was called xy in rectangular coordinates, that same point is called r theta in polar coordinates. Okay, it's just a different coordinate system is all it is. Let me show you the differences in what graph paper would look like. I got a new pen for my tablet, and the tip of the pen is more of a harder plastic instead of a soft rubber. So I hope that the clicking noise is not too annoying for you. Okay, so in rectangular coordinates, let's write up here, rectangular, or by the way, you're probably familiar also with this name. Besides rectangular coordinates, it's also called Cartesian coordinates. So this would be rectangular or Cartesian graph paper. Okay, so you're familiar with this ever since you were a child, right? You have an x-axis. Well, first you have the origin, and then at the origin through there you draw a horizontal x-axis and a vertical y-axis, right? And then you have a grid. I'll try to do this fairly neat, but it's not going to be perfect. Okay, so that's what rectangular graph paper looks like, correct? Okay, now let me show you, let's shrink this down a little. Let me show you what polar graph paper would look like. So you see what we have there is, first of all, there's only one axis, and it's not a line, it's just a ray starting from the origin and going horizontally to the right. Okay, so there's only one polar axis. And then, instead of grid lines running vertically and horizontally, you have instead some circular lines, okay, at the different distances out from the origin. In this picture, there's a circular line with a radius of 1, a circular line with a radius of 2, and so on. Circular line with a radius of 3, okay. And there's also radial lines here emanating from the origin at, whatever angles you would like. You could put these in. These are in the normal useful angles. Here we have pi over 6, pi over 4, pi over 3, pi over 2, and so on. Okay, so that's what polar graph paper looks like. Now, you can certainly draw polar coordinates on rectangular graph paper, and many people do that. You just have to be careful. It can get confusing because you're thinking in one way and drawing that on a picture that's intended for a different way of thinking, and so it can get confusing. Okay, so here's what we're going to do. Let's plot some polar points. I should say some points in polar coordinates. Okay, so let's plot the point 1, comma, pi over 4. And let's call that point A. Now, remember that the first coordinate is the radial coordinate, and the second coordinate is the angular coordinate. You got to keep that straight. Just like in Cartesian coordinates, you have to remember the first coordinate is always the x coordinate and the second coordinate is always the y coordinate. Okay, so now to plot point A, here's what I would do. I'm going to show you two ways you can do it. Okay, you can say the radial coordinate is 1, so I'm going to go out along the radial axis, a distance of 1. Okay, let me see actually if I can do that like this. Let's see if this will work. There we go. I can go out a distance of 1 and then go counterclockwise an angle of pi over 4. And that would be where our point A would belong, right there. Okay, so that's one way to do it. You go out radially along the axis, and then you rotate that ray an angle of theta. Okay, that's personally not how I usually do it. I like personally to do it in the opposite order. What I do is I first do the angle.
Did you get one wrong?
So I draw a ray from the origin at an angle of pi over 4
Ooh, I'm gonna beat Kelly.
with the axis. There we go. Okay, so I set the angle first. And then I shorten that ray to a length of 1. Which means it would look like this. There we go. And then again, my point would be right there. Okay. Let's do a couple more points here. Let's do in green. We'll do point B at the coordinates 1.5, comma, pi. Okay, so I'm going to go an angle of pi, and then I'm going to go out a distance of 1.5. And that's where my point will be.
Yeah, it's like Catherine dreaming.
Okay. Let's do the point 2, comma, negative pi over 3. We'll call that point C. Okay, so my angle is negative pi over 3. This time I'm going to go clockwise, not counterclockwise. Okay, a distance of pi over 3, I mean an angle of pi over 3 rather. Negative pi over 3. Got to get it right.
Yeah.
Okay, and then I'm going to go out a radial distance of 2. And that's where my point will be.
When is the high school American high school? That's kind of weird.
That was right here. Let's do one more. This will be point D. And the coordinates will be negative 1, comma, pi over 4. Okay, so I go an angle of pi over 4. And now, this is interesting now. The radial distance says negative 1, right? And that's okay. That's allowed to be negative. It just means that I'm going to draw the ray this direction, backwards, if you will, a distance of 1. And so there's my point, D. Okay, that's how that works, plotting points in polar coordinates. Now, I want to point out something to you, that these are not unique. Okay? In rectangular coordinates, if I located a point, there's only one pair of coordinates that would give me that point. But in polar coordinates, that's not true. For instance, point D that we just plotted at negative 1 pi over 4, let's write that in the picture here, negative 1 pi over 4. So I went an angle of pi over 4 and then backwards a distance of 1. Okay, that would have been the same location if I had gone an angle of what? 5 pi over 4 and then go forward a distance of 1. See what I'm saying? So these coordinates are not unique. Negative 1 comma pi over 4 is the same thing as positive 1 comma 5 pi over 4. And of course you could also add any multiple of 2 pi to that angular coordinate and you'd end up at the same point. Okay, so that's interesting. You got to be a little bit careful about that. Alright, so that's plotting points. Now let's practice plotting some equations in polar coordinates. Okay, let's graph this equation. R equals cosine of 2 theta on the domain 0 to 2 pi. Let's think for a minute before we start graphing.
I would be able to understand what you said.
You're used to seeing things like this in calculus, right? Graph y equals 5x plus 2 on the domain 0 to 5 or 0 to 6 or whatever you want. Let's write 0 to 1. Okay, you're used to seeing things like that, correct? All right, so here's what I want to point out. The equation, you see, gives you one coordinate in terms of the other. In Cartesian coordinates, our coordinates are x and y. And so when we say an equation in Cartesian coordinates, that's an equation that relates one coordinate to the other. This relates it relates y to x. Y is always equal to 5 times x plus 2. Okay? Same situation here. Whoops. Same situation here. Our two coordinates are r and theta. An equation is something that relates the two coordinates. This is relating r to theta. It's saying r is always equal to the cosine of twice theta. Okay? Remember that this, remember this variable is called the independent variable, and this is called the dependent variable. So in our polar equation, we have theta as the independent variable and r as the dependent variable. Does x always have to be the independent variable and y the dependent variable? No, but usually it is. In polar coordinates, does theta have to be the independent variable and r the dependent variable? No, but it usually is. Okay, now let's talk about the domain. In rectangular coordinates, that interval 0 to 1, that domain refers to which variable? Always refers to the independent variable. So in polar coordinates, when we're given the domain 0 to 2 pi, okay, that refers to the allowable range for theta, because that's the independent variable. Does it have to be 0 to 2 pi? No, it could be anything. Okay, but let me point out to you, it never makes any sense for the domain to have a length longer than 2 pi, because if you use angles in a range more than 2 pi, then you're going to start repeating yourself anyways, and so that would be a waste of time. Okay, so let's go ahead and graph this now. How can I do this? I can do this by just plotting points. Okay, let me make a little table here. We'll just have our independent variable and our dependent variable. Okay, and we'll plot several points. So, when theta is 0, what's r going to be? It's going to be cosine of 0, correct? Which is going to be 1. So that we need to place a point at 0, 1. Okay, let's go ahead and do that.
Wow.
So that's going to be right here, correct? An angle of 0, a radial distance of 1. Okay, let's do pi over 6. R would be the cosine of pi over 3. The cosine of pi over 3 is a half. So I'm going to go to an angle of pi over 6 and then go out a distance of 1/2. I'm going to have a point right there. Okay, let's just continue. Pi over 3. R will equal the cosine of 2 pi over 3, which is negative 1/2. So where's that point going to be? Sorry, I skipped pi over 4. Why did I do that? Let's do this for a minute. I'll just move these down. I won't plot that point yet, okay? But there's no sense in erasing those. Let me put in here pi over 4. Okay, R will be the cosine of pi over 2, which is 0. So that will be right there at the origin. Notice that when R is 0, it doesn't matter what the angular coordinate is. Any angle but a distance of 0 from the origin is going to put you at 0, right? Okay, then we have pi over 3, negative 1/2. So here's the pi over 3 line to help me. I go a distance of negative 1/2. That's going to be right here. Okay. And then what should I do next? Let's do pi over 2. R would be the cosine of pi, which is negative 1. So pi over 2 right there. We go a distance of negative 1. Radial distance, that's going to put me right there. All right, just keep continuing. Let's do 2 pi over 3. R would be the cosine of 4 pi over 3, which is negative 1/2. 2 pi over 3 is the angle. The radial distance is negative 1/2. Puts us right there. Okay. 3 pi over 4. R will be the cosine of 3 pi over 2, which is 0. So that's going to put me back at the origin again. Let's do next 5 pi over 6. You might get the idea, but I just want to do a thorough example here. 5 pi over 6. R will be the cosine of 5 pi over 3, which is positive 1/2. So 5 pi over 6, go a radial distance of positive 1/2. That'll put us right there. Okay, and then let's do pi over 2. All right, let's see. R will equal the cosine. Sorry, I knew something was wrong. We're not at pi over 2. We passed that a long time ago. It's pi. There we go. R will be the cosine of 2 pi, which is 1. So there's pi over 2. Radial distance of 1 puts us right there. Okay, now I'm going to go ahead and just fill in several more points. And I'm going to fast forward to try to save you some time. Okay, I filled in several more values. Let's just plot those points that I just filled in, okay? We left off at pi 1. Oh, so I should be more careful. That's the point 1 pi, right? This is something you got to be careful about. So let me pause for a minute to explain this. We've got to be careful about this. When you're doing rectangular coordinates, remember, you can write the coordinates as x, y. And the equation usually has y written in terms of x. So when you do a table of values, you write x on the left and then y. Notice the order there is the same as the order when you write the coordinates down. In polar coordinates, you need to be a little bit more careful. The coordinates are written r comma theta. But the equations usually have r written in terms of theta, which means your input will be theta and your output will be r. You see, the order's different, so you just got to be careful of that. So for instance, this point right there is technically, that's not the point pi 1, that's the point 1 pi. Okay. All right, now I filled in the rest of the table. Let's just plot the points. When theta is 7 pi over 6, r is positive 1/2. We get this point. When theta is 5 pi over 4, r is 0, so that's going to be at the origin. When theta is 4 pi over 3, r is negative 1/2, so that's going to put me here. And when r is 3 pi over 2, theta is negative 1, that's going to be there. When r is 5 pi over 3, theta is negative 1/2, right there. And when r is 7 pi over 4, theta is 0, that'll be back at the origin. I mean r is 0, sorry. When theta is 11 pi over 6, r is 1/2. And then this is redundant. I'm back to 2 pi. That's going to be the same as when theta is 0. That's going to put me back right there again. Okay, so there's a bunch of points. Now, you have to remember the order in which those points came in order to sketch the graph. So, we started right here, and the points came up in this order. Went like this. I'm putting a bit of a curve to it because I already know that the graph is actually curved, so I'm not going to just connect them with straight lines. That's just because I'm familiar with this already. So it went like that, then through the origin, then it went down here, down to there, curved back up to here, back through the origin, over to here, looped around, back to the origin, and then it went up here and looped around, back to the origin, and then it went, I've missed a point somehow, sorry. I never had this one plotted. Okay, so then it continued. Sorry, no, sorry, I was right to begin with, I'm sorry. I shouldn't have put that last point in there. Okay, because then it went to this point and then back to there. There you go. That's what it is. It's kind of like it's like a flower with 4 petals. Okay. Now I'm going to delete my picture and instead I'm going to paste in the picture that is in the book. It's a much nicer picture. There's the exact same graph in the book. Looks bigger because it's zoomed in. Okay. This is the line r equals 1. This is the line r equals 1/2. Okay. And those numbers are the order in which the points came up. Okay, there's point 1, and then point 2, and then point 3, 4, 5, 6, and so on. Okay? So, that is the graph of r equals cosine 2 theta. I'll show you another graph. I'm not going to drag you through it in as much time because this lecture will be way too long, but let me just show you for the sake of an example. Okay, let me show you a graph of r equals 1 plus cosine of theta on the closed interval from 0 to 2 pi. Okay, there's the table of values. We don't have to run through all of those calculations, but you can check them if you want. Okay, and here's the graph. Notice in the table of values they got a little bit lazy at the end. They didn't put in 2 pi, but that's because they knew that it's going to coincide with the first line in the table anyways. Okay, let's just run through this in order here. I'll draw arrows to these. Okay, so the first point would be this one, 2, 0. Okay, and then after that you have 1 plus root 3 over 2, comma, pi over 6. Let's do it like this. I'll number them, okay? So that's the first point, and then that's the second point, and then the third, and the fourth, the fifth, sixth, seventh. Which point is that? Seventh one. Let's just test ourselves. It's right here. 1 minus 1 over root 2, comma, 3 pi over 4. Okay? And then here's the 8th point. And then the 9th point is right there. Sorry, is right here. So that's the origin. Okay. And then the 10th point, 11th, 12th, 13th, 14th, 15th, 16th, and then there would be the 17th point would be back here again. Okay? So that's the graph of 1 plus cosine theta. That is called a cardioid because it resembles the basic shape of a heart, a little more rounded, and it's on its side. Okay, it's a heart laying on its side. It's not pointed at the bottom. It's rounded, but that's what those are called, cardioids. Okay, so that's how you graph things in polar coordinates. Now, how do we convert between polar and rectangular coordinates? Let's go through that. From rectangular coordinates to polar coordinates is fairly easy. Let me show you why. Let's look at a point in rectangular coordinates. Let's say right here. Let's just call it x, y. Okay, and then in green, I'm going to write r theta. If you knew x, y, could you calculate r and theta? I think you could. First of all, for r, you would just have to use the Pythagorean theorem. You see, you have here a right triangle. You see, and this length is x, and this length is y. So how long is r? Well, you can write down r squared equals x squared plus y squared. Now, technically, that would mean r is the square root of x squared plus y squared. People don't normally bother writing that down. You won't see that written in a book. In the book, it'll just say r squared equals x squared plus y squared. Okay? And what would be theta? Well, using trigonometry, looking at that same right triangle, you would say that tangent of theta would be y over x, opposite over adjacent, which technically means that theta is the arctangent of y over x. Again, you won't probably ever see that written down in a book. It'll just say tangent of theta equals y over x, because the truth is theta doesn't have to be the arctangent of y over x. It could be the arctangent of y over x plus any multiple of 2 pi, and there's also some other possibilities too. Okay, so you'll just see it written like that. Okay, so let's convert a point from rectangular to polar coordinates. Let's suppose that point in rectangular coordinates is 5, 5. How would we write that in polar coordinates? Myself, let's see, what do I think is better, to find the r coordinate first or the theta coordinate? I suppose it doesn't matter. Let's just go ahead and find the r coordinate. Okay, so I would write r squared should equal 5 squared plus 5 squared, which is 50. Okay, there we go. R squared is 50. So what are some possibilities? I can say r is the square root of 50. That would be 5 root 5. And one other possibility is I could also say r is negative 5 root 5, couldn't I? Because either way, then, r squared would equal 50. So either of those would work. Okay, that's what I wanted to do this. I'm pointing out to you that there's two possibilities for r. Okay, now let's find theta. I would write tangent of theta equals 5 over 5, which is 1. So for theta, I can write any angle that has a tangent of 1. Obviously, an easy answer would be pi over 4. But I want to point out to you, I could also write 5 pi over 4. That would also work. And I could also write negative 7 pi over 4, by the way, also has a tangent of 1. So you see there's actually infinitely many choices that I could put for theta. Okay, so now how do you navigate this fact that there's two choices for r and lots of choices for theta? You just have to be careful and pick a pair that works. For instance, it would work if I wrote 5 root 5. Whoops, I didn't know why I put that comma there, sorry. If I wrote 5 root 5, comma, pi over 4, that would be correct. Because you go an angle of pi over 4, and you go radially a distance forward of 5 root 5. So that would work fine. It would not work if I wrote negative 5 root 5, comma, pi over 4, because that point would be back here. But it would work if I put negative 5 root 5, comma, 5 pi over 4. That would work, because then I would be doing this. 5 pi over 4, and then go backwards a distance of 5 root 5. It would put me there. So you just have to be careful. You'll always have two choices for r and lots of choices for theta. Do you want to avoid that problem? Okay, I'll show you an easy way to avoid it. Always pick the positive choice for r, and pick the choice for theta that would be between 2 pi, so in other words, I'd cross out that one, and also would face you forward into the quadrant that you want to be. So since this point is quadrant 1, whatever, I should say it like this, whatever quadrant the point is in, pick the angle that ends in that same quadrant. So I would cross out this one. So the easiest answer, and you can always follow that rule, okay? Pick positive value for r, and pick the angle that ends in the quadrant where the point is. So for me, I would label that point as 5 root 5 comma pi over 4. Okay, that's how you convert a point from rectangular to polar coordinates. How do you convert an equation from rectangular to polar coordinates? Okay, let's look at that. Okay, suppose now I have the equation y equals x squared. And I want to convert that. Let me write that in blue, okay? And I want to convert that into a polar equation instead of a rectangular equation. Okay? Okay, that's pretty straightforward. I just need to show you something again. Okay, remember these two equations up here. Those are going to be very handy. Let's not forget those two equations up there, okay? But let me show you two other ones that are also important. So let's scroll down here for a second. Okay, let me put here an XY axis again. Or actually, no, let's do this. Let's put, I'm going to put a picture of the polar graph paper, okay? Give me 1 second here. Where was that picture? Here it is. Okay, look at that picture for a minute, and let's just throw a point on there. Right here, let's say. Okay, so that's r theta. So this distance is r. This angle is theta. Let's find x and y. This is actually really easy. You know how to do this. Look at this right triangle. There's x, there's y. Isn't it true that x is r cosine theta and y is r sine theta? You already knew that from trigonometry. Okay, so I'm going to write down those two equations. Those are going to be very helpful. Let me just take a second to get rid of this picture. Okay, so I want you to also remember this, that x equals r cosine theta. Whoops, I forgot the c. And y is r sine theta. So those are also very important, those two equations. Because if you have something like this here, okay, it's really easy to convert that rectangular equation into a polar equation. All you have to do is replace y with r sine theta and replace x with r cosine theta. And now you have an equation with r and theta instead of x and y. And let's just solve that for r. So we have r sine theta equals r squared cosine squared theta. Let's divide both sides by r, which we can do as long as r is not 0. And then let's divide both sides by cosine squared theta as long as that's not 0. And so there we have our polar equation. R equals sine theta over cosine squared theta. Or if you prefer, that's also equal to tangent times secant. Look at that for a second. Do you agree with that? Tangent times secant would be the same thing as sine over cosine squared. So let's go ahead and write it that way. Okay? And there you go. You already knew that this was a parabola, and in polar coordinates that parabola looks like this, or the equation of that parabola, let's say. Okay? Let's do one more here like this. Let's convert xy equals 1. That's a hyperbola. Okay, so we just replace x with r cosine theta, and we replace y with r sine theta. So we have r squared times cosine theta sine theta equals 1, which means r squared equals 1 over cosine theta times sine theta. So what I'm going to write over here for my equation is I'm going to write r equals 1 over, actually, you know what I'm going to write instead of 1 over? I'm going to write secant times cosecant, and then it's going to have a square root. Because, not because I'm changing to secant cosecant, but because, sorry, secant times cosecant, that's what r squared equals. So for r, I'm going to write the square root of secant times cosecant. Okay, that's very straightforward, because you just replace x with r cosine theta, and you replace y with r sine theta. Okay. What would be the domain of that, by the way? In rectangular coordinates, the domain is, I don't know if you remember or not what this graph looks like. Let me show you the graph here, okay? Let me paste it in here. I think I have it saved on my computer. Let's see. No, I don't. Okay, so give me a minute. I'm going to need to go grab it off the internet. Okay, there we go. That's the hyperbola, xy equals 1. Okay, in rectangular coordinates, what's the domain? The domain is, sorry, that's not even right. The domain is everything but 0. So it's all negative numbers, union all positive numbers. That's the domain in rectangular coordinates. In polar coordinates, what's the domain? So in other words, if I was to have here a ray emanating from the origin, okay, when does that ray not cross the blue hyperbola? Well, when theta is 0, it doesn't cross. In fact, you might recognize that as being an asymptote now, right? So there is no points when theta is 0. Remember that. I'm not going to write it down right now. Just remember. Then as this opens up, it's crossing the hyperbola. Where is it crossing the hyperbola? At a distance of square root of secant theta times cosecant theta. But when I get up here to pi over 2, look, it's not crossing the hyperbola. So pi over 2 is not in the domain. In fact, there's no points for any of these angles in quadrant 2 either. That's not part of the domain. We don't start coming across the hyperbola again until quadrant 3. And then nothing again for quadrant 4. So what's the domain then in polar coordinates for that hyperbola? The domain is everything, this is for theta, remember, everything between 0 and pi over 2, and also angles between pi and 3 pi over 2. Okay? Let's do that same little domain exercise for our previous example with the parabola. Let me stick in a picture of the parabola here. In rectangular coordinates, what was the domain? All real numbers, right? X could be anything. But in polar coordinates, what is the domain? Let's do that same visual exercise we did before. In polar coordinates, the domain is these angles. So what is that? That's 0 to pi, correct? So that would be the domain in polar coordinates. 0 to pi. Okay? So that's a lot of practice there, converting from rectangular to polar. We converted a point, and then we converted two equations, and we used those equations in the red boxes to help us. Okay, let's practice converting from polar to rectangular. Okay, now for points, that's very easy. We just use the same equations from those red boxes. Okay, suppose I have the point in polar coordinates. Suppose we have r is 3 and theta is, let's just do pi over 2, okay? All right, then for rectangular coordinates, just remember x equals r cosine theta and y equals r sine theta. So what would these be? X is going to end up being 3 times 0, and y is going to end up being 3 times 1. And so your point is 0, 3. Very simple, very straightforward. Okay, converting an equation, a polar equation, into a rectangular equation is a bit harder. Okay, let me write down this polar equation. R equals 2 over sine theta minus cosine theta. Now, in theory, one way I could go is I could say, well, remember, r squared is cosine squared plus theta squared. Oh, sorry, that doesn't even make sense. Why did I even say that? What I meant to say was r squared equals x squared plus y squared. So r is the square root of x squared plus y squared. I mean, this is just in theory. This doesn't actually help you. Okay, but you could do that. You could say that's r, and then equals 2 over, and then you could say tangent of theta is y over x, so you could write sine of arctangent of y over x minus cosine of arctangent of y over x. Now, unfortunately, this is not helpful. Number one, it's too complicated. But number two, the other problem is, remember that r could have been negative square root of x squared plus y squared. And theta doesn't have to be arctangent of y over x. Remember how we went through that there's lots of different possibilities? So that's the problem you run into. So what you want to do when converting a polar equation to a rectangular equation instead is you want to use these two equations right there. X equals r cosine theta, y equals r sine theta. And you want to try, this might be easier said than done, instead of having just r by itself, and instead of having just some trig things about theta by themselves, you want to try using algebra to rearrange things so that you can try to get the product r cosine theta and the product r sine theta to show up. In this example, that's pretty straightforward because we take r equals 2 over sine theta minus cosine theta. Let's multiply both sides by sine minus cosine. So we get r sine theta minus r cosine theta equals 2. And that's very helpful because r sine theta is y, r cosine theta is x. So we have here y equals x plus 2. That is in fact a straight line. Okay. That would look like this.
Yeah.
Roughly like that. What's the domain in rectangular coordinates? The domain is all real numbers. What's the domain in polar coordinates? It's going to be every angle between 0 and, oh, well, that's, no, I don't think that's even true. Just a second. It's every angle from pi over 4 to 5 pi over 4 because the slope of that particular line is 45 degrees. Okay, that should actually be.
Yeah, but I'm like, who put Bernie Sanders in between Godzilla and King Kong?
That should actually be green.
Oh no.
Okay, the last thing I want to do is just show you some nice pictures here. Okay, this is just straight out of our book. A circle centered at the origin is a very simple equation in polar coordinates. It's just r equals a. It's all of the points that are a distance of a from the origin. That's the circle of radius a centered at the origin. Okay? You can see over here equations for circles with radius a centered in different places. Okay, and they just get those equations just from the corresponding rectangular equation that we technically should already know. Okay, these shapes are called Limisons. You've seen this one before, the cardioid. Okay, this is a little bit misleading. Let me make sure you're reading this correctly. That's not the equation of the cardioid. We've already seen the equation of the cardioid, right? The equation is like this. For all of these pictures, the equation is like that. a number plus or minus a number times cosine. The one that we had was 1 plus cosine theta. Okay, and what they're saying here is that if that first number a is smaller than b, then you get this loop inside there. Okay? If a is the same side as b, like it was for us, they were both 1, then you get a cardioid. Okay? If a is between b and twice b, then you get what they call dimpled. It's like a cardioid, but this point part right there has kind of been pushed out. And if a is bigger than twice b, then you lose that dimple entirely and it becomes more like a circle that's flattened at one end. Okay, those are called Limisons. These are called Rose curves. We actually saw this one earlier in one of our examples. Okay, once again, the equation for these types of curves are always like this. For if it's symmetric about the x-axis, it could be like this. If you want it to be symmetric about the y-axis, okay. But the point is, it's always a number times cosine of a multiple of theta. This is the one we did in our example, and notice it has 4 petals, right? If you did a sine 2 theta, it still has 4 petals, but you see it's symmetric about, well, I guess that particular one is symmetric about both axes, but you see how it's rotated a little? Okay, look at these two. When you have cosine 3 theta, you have 3 petals, sine 3 theta, 3 petals. What is the rule there between that number in front of theta and the number of petals? Okay, it's listed right here. If there's an even number of petals, sorry, let me say that one more time. If n is even, then you double n will tell you how many petals it's going to have. Okay? And if n is odd, then that number n is exactly the number of petals you're going to have. Okay, and then just a few more. Here you have what's called a Lemniscut. It's like an infinity symbol. And here's something very similar, but more flattened on the ends, called an 8 curve. These down here are really fancy. Things like that. You don't need to try to make sense of those pictures. I'm just showing them to you just to see what kind of pictures can be created by relatively simple polar equations. Don't try to make sense of those pictures. They're very complicated. Okay? This one's easy to make sense of, though. A spiral. Very simple equation. R equals theta. What's that tell you? It tells you as the angle opens up more and more, the distance from the origin gets bigger and bigger. So what are you going to end up with? You're going to end up with a spiral. Okay? And you can see all these pictures in the book. They're just taken straight out of the book. All right, now this lecture's been long, and you might notice that several of the lectures are long. That's because this is a 4-unit class, not a 3-unit class. But I'm only posting 3 lectures a week, so the lectures are longer than a normal 3-unit class would have. That's why. Okay, keep up with the homework. I've been posting homework for you to be doing as we go along. So there's now up to assignment. Let me check real quick for you. For this class, I know you haven't had to turn in anything yet. The first assignment has not come due. It's due in a few days, but I've posted 3 more to take us over the next 2 weeks. So over the next 2 weeks, you'll be finishing assignment 1 and doing 3 more. So make sure you keep up with that. Although you can't do the fourth one yet, but as of right now, you can go ahead and accomplish homeworks 1 through 3. Okay, take care.